Hello, everyone, and welcome to, I believe, the third edition of our extremal and probabilistic webinar this year. And we will have as our speaker today, Rajko Nenadov, who is at Google at the moment. And Rajko will tell us about his recent new proof of the KLR conjecture, sorry. So, Rajko, what we usually do is that we let people ask questions as the speaker goes. Is that fine with you?
Yeah.
And if anyone has any problem with their audio, then please type the question in the chat and I will read it out to Rajko. Okay. So Rajko, please.
Cool. Thanks a lot. Yeah, so the first part of the talk will be mostly kind of motivating the KLR conjecture. Oh, hold on, let me just share the screen first. Okay, good. So the first part of the talk will be mainly about motivating the KLR conjecture. So if you get lost in the first part of the lecture, the second part or the talk, the second part will be a bit useless. So do interrupt me if anything is unclear in this first half an hour, and then keep interrupting me when we get to the proof. Okay, so let me start. As advertised, I want to tell you a bit about this new proof of the KLR conjecture. And first, I want to tell you what a KLR conjecture is. So the way that the KLR conjecture is usually motivated is through this through semi-reduced regularity lemma and its application in subgraphs of random graphs. And because of that, the conjecture has this reputation of being sort of more a bit on the technical side. So I want to motivate it a bit differently and convince you that it's actually a really natural conjecture. Almost not technical at all. Now, so even if you know what a conjecture is, I hope you will hear something at least a bit new in this first part. So let me start. A KLR conjecture is a conjecture about random graphs. Now there are two models of random graphs that we will consider today. One is the uniform model, GNM. So we start with a complete graph on n vertices, and we choose m edges completely uniformly at random. Right? So if this is our complete graph on 6 vertices, and we choose, say, 6 edges, we might end up with something like this. A related model is the GMP binomial model. So again, we start with the complete graph on n vertices, but now instead of having a fixed number of edges, we have this parameter p, which is a number between 0 and 1. We just take each edge of this complete graph with probability p independently of all other edges. So for each edge, we just toss a coin, and the coin with probability p tells us take the edge, 1 minus p, don't take the edge. So we toss a coin for this one, we take it, don't take it, don't take it, take it. So you can do it kind of one by one, you can do it all at the same time. You can toss a coin for the single edge multiple times with some small probability. As long as you end up with each edge being there with probability exactly p, it's fine. And the reason why it's called binomial is because the number of edges is binomially distributed. Okay, so which model to choose? When we take p to be m over n choose 2, you can think of GMP as being an approximation of GNM. So in expectation, such GMP will have exactly m edges. In reality, it's not very likely that it will have exactly m edges, but it will have roughly m edges. Now, what's the advantage of GMP? It's significantly easier to analyze. And in most cases, a result about GMP would just transfer to GNM in a rather standard, like using some standard techniques and tools. What's the drawback of GMP? The drawback is that some of the probability mass is wasted. So in particular, the GMP will be empty with some small probability, but as we will see, this is actually quite a significant probability. So the main question we want to ask today is, what is the probability that a random graph, GNM or GMP, does not contain a given graph H? And we will think of H as being a fixed graph. So we allow any constants to depend on H, and N is as large as we want it to be, or as we need it to be. Good, so let's consider what happens in GMP. The probability that the GMP is H-free, it's equivalent to the following. So we look at all possible copies of H inside complete graph on n vertices, and we look at this indicator variable that this particular copy of H is not contained in GMP, right? And we need this to happen for every possible copy of H. So this is, by the definition, what we mean by GMP is H-free. Now, using Harris inequality, we can lower bound this with a product of each individual of the probability of each individual such event, and the probability that we don't see one particular copy of H in GMP is exactly 1 minus p to the number of edges of H. Now, how many copies of H in complete graph on n vertices are there? Roughly n to the number of vertices of H, and then a simple calculation tells you this is actually e to the minus something of order the expected number of copies of H in GMP. Okay. Now we can repeat the same, but instead of looking at this at bounding the event that GMP is H-free, we're going to look at the event that GMP is H prime free for some H prime, which is subset of H, right? So this is clearly a lower bound on the probability that GMP is H free, right? And repeat exactly the same calculation as before, now with H prime replacing H. And what we end up is that this is at most, at least e to the minus the expected number of copies of H prime. So putting all together, we have that the probability that GMP does not contain H is at least e to the minus this value. So we look at all copies, all possible subgraphs H prime of H, and we choose the one which in expectation appears the least number of times. And it turns out that this is correct, at least that the exponent, the order of the exponent is correct. And the upper bound was shown by Janssen, Uchek, and Ruchinsky in 1988. So in general, this tells this is the first step towards determining, towards answering this question, and it's already quite satisfactory. So we know this probability, or we know the order of the logarithm of this probability. So let's look at example. Suppose that this is our graph H, and let's see how this value, which I'll call phi, how it changes as p goes from 0 to 1. So up to this value, up to p being 1 over square root n, this minimum here is attained by triangle, right? And then phi is then of order n cube p cube. After this point, so in other words, like the least frequent subgraph in expectation, the least frequent subgraph of H in GMP is this triangle. After this point, it's just a single edge. Now, so what does this mean here? How did we calculate this? The probability that H is not subset of GMP, subgraph of GMP, we look at this least kind of likely subgraph of H prime, and then we just bound the probability that that particular H prime does not appear. And this regime here, that least likely subgraph is actually a single edge. And therefore, our bound of H not being subgraph of GMP is really determined by GMP being empty graph. Now let's for a moment think about what this means if we look at GNM. Well, in GNM, this makes no sense because in GNM, we know that we have exactly M edges and there is no randomness there. So at least kind of looking at this picture here and how we calculate this phi, so there is something slightly funny going on here, at least in this reasonably kind of high range of P. Okay, so let's look in more details now, the GNM case. Now, first thing to notice is that, so neither the Harris inequality nor Janssen-Nucek-Kruczynski results apply directly in this probability space. Now, there is a standard workaround, and that's what I said before. We, instead of looking at GNM, we look at GMP with P being M over N choose 2, and use concentration number of edges to deduce something about GNM. And the way it goes is, so this is what we have. This is what we had from before. Now to transfer that to GNM, it turns out that the upper bound transfers more or less in the same form. So we'll have some constant C in front of this expression, but that doesn't really matter. And for the lower bounds, we have the same thing as before, plus some error term. And this error term really comes from bounding the probability that the number of edges deviates more than some epsilon n squared p from M. And the problem here is that this term here can become negative if this value here is of order n squared p. Right, so we'll have e to the minus something of order n squared p minus e to the minus something of order n squared p, and it turns out that the constants are not in our favor, and for some ranges of p, and therefore we just by using this result from GMP, we just get that the probability of H not being in GNM is at least 0, but we knew that without any calculations. Right, but this precisely happens at this range of P or M, which we said it's a bit questionable on this picture before, right? So just to remind you again, there was this in this range of P, when the edge becomes the least likely graph, we bound the probability of GMP not containing H by. So we're just looking at the probability GMP is empty, and in GNM that makes no sense, and this kind of confirms that right something else is going on. Okay, so what?
Sorry, Rajko. So why didn't you have that problem on the right hand side? I didn't get that.
It's a different way of proving the upper bound and lower bound, of transferring upper bound and lower bound.
Okay, but so that's a completely different way which you.
Yeah.
Okay, thanks.
Oh shit. Oh, I just have a question. So, but in this situation, like you can have genuinely different behaviors. So you'd expect some, like isn't if it's bipartite, then aren't you sort of like H bipartite? Then you're stuck, or if it chromatic number, then maybe.
Right, that's precisely where I'm getting at. So I just want.
Oh, I see. Okay. So, but yeah, it's complicated for some reason. Yeah. Okay.
Yeah. So yeah, I'll get there in a second. Right. So the situation we have now is that the probability of GNM not containing H is really the same as what we had before, for M being not too large, right? And by not too large, I mean at most this value here, where this M2, the so-called tour density of H, is defined as the smallest number such that this is of order M for every M bigger than this value. Good. Right, and the reason why it doesn't transfer past this point is because this is no longer true, and that's what's shown by Balog, Morris, and Samoti, that if H is a bipartite graph, then H not appearing in GMP actually starts to grow super exponentially in M when M goes away from this value here. So as M keeps growing, it will at some point reach the point where this Janssen-Uczak-Rutschinski result will tell us that the probability of not containing H is exponentially small in M. And then if M keeps growing, this probability will come super exponentially small for bipartite graphs. Right, which tells us in a way that this situation that we had before, that the way we calculated this, the lower bound and the probability of H not appearing in GMP, by saying simply, well, it's at least the probability to sample an empty graph. That's kind of that. This shows that is the main reason for H not appearing in GMP for this regime of P. Right. So then the situation is like this. Now, what happens when H is non-bipartite? Well, how we calculated that H is not in GMP using the Harris inequality. That's one way to show that the GMP or GNM do not contain H. It turns out that when M becomes so large, there is another reason why GNM does not contain H, and that's that if H is non-bipartite, the GNM is bipartite for probability to the minus some order of M. Right, and if GNM is bipartite, then it will not contain H. Right, and the way to see this is, we just count the number of edges going across divided by the total number of edges, and we get e to the minus Cm. Now, what's the problem here? What if we actually sample such a graph? Okay, it has the correct number of edges because the number of edges is fixed, but it has another parameter. It has another very atypical feature for random graphs, and that's that it has this really, really enormously large independent set. Right, but it has an independent set of size n/2. So then the natural question is, well, if we know that the number of edges is not the main culprit for being H-free, maybe it's this atypically large independent set. So what happens if we want to calculate the probability of, say, this pentagon not appearing in GMP condition on GNM not having large independent set? It turns out that this is still e to the minus Cm, but now it's slightly more subtle. So what we're gonna count the graphs with M edges such that instead of having these two large independent sets, we're gonna put something in between. So we're gonna put a graph which is triangle free, has some order of n many edges, and no large independent set. Right now, you can calculate such a graph. You can construct such a graph easily, somewhat ironically, using random graphs. But anyway, once you fix such a graph here and here, you still have plenty of choices in between that it doesn't really impact the total number of choices of such graphs, and you again end up with the probability of not containing pentagon, even condition at not having large independent set, to be e to the minus C times M. And now here's the point. The point is that the large independent set is the extreme case of an event that the number of edges in a large subset is significantly smaller than the expectation. And you should make an analogy with the GMP case. So in the GMP case, the probability of GMP not containing H and this kind of large range of P was to calculate the probability that P has no edges. Or that's the extreme event of the extreme case of an event that GMP actually has significantly less than the expected number of edges. And the same happens here. Instead of just forbidding a large independent set, what we should forbid is a large set having significantly less edges than what we should have there in expectation. Or in other words, just condition on GM or GNM actually being a random graph, like having a nice, reasonably even distribution of edges. And that's exactly what the Kuhakawa-Uczak conjecture says. So let me state formally a version of it. for any graph H and any beta and C, which are some small numbers. Okay, C actually doesn't appear anyway. Anyway, so for any beta, if there exists some epsilon such that if M is significantly larger than this point where Jansen-Ucha-Kruczynski tells us that the probability exponentially small in M, then if we condition on this on this event U epsilon, the probability of H not being in G and M is at most beta to the M. And what is U epsilon? It's exactly what I said before, that for every vertex subset of size some epsilon n, we see at least say half of the expected number of edges. So this is a reasonably weak notion of uniformity. But uniform edge distribution is the property of random graphs. And what the conjecture says is that if we condition G and M actually looking like a random graphs, then we get that the probability is matching the one for bipartite graphs. Or in other words, a typical H-free graph is not random looking. Now, if you know what the KLR conjecture is, you will know that this is not how it's stated. Qualitatively, it's the same as the actual conjecture, except that the conjecture is for applications stated in a multipartite version, as a multipartite version. Okay, so up to this point, I kind of tried to motivate why is it natural that if you start with G and M and you go, why it is natural then to actually even look at G and so if you start with G and P, why is it even natural to look at G and M, and then so how can one reasonably naturally get to this to this conditioning? Are there any questions about this? If not, then
I have a question. Sorry.
Yeah.
So so the lower bound we also expect to be e to the cm. Sorry, minus cm here. Or, just trying to think about like what exactly is the event that's dominating in this situation.
I mean, this is what do you mean?
Yeah. So what should this probability that's at most beta to the m? What if it's a equality? What should it be?
I don't know. I just kind of so the whole point here is to show that what comes from the sort of what comes from Jansen-Ucha-Kruczynski is not that's not the correct value. You can go a bit below it.
Right.
What's the correct value? Actually, I don't know. I don't even have a guess.
Yeah, yeah, very interesting. Yeah.
Yeah. So here, really the point is just to have like just to show that
yeah, super
e to the minus order of m is not the correct. It's not that the log, even the log is not correct.
Right.
So a bit about history. In the book Random Graphs from 2000, Jansen-Ucha-Kruczynski called this conjecture one of the most important open questions in the theory of random graphs. And it has attracted a significant attention over the years. And until it was finally proven in 2015 by Ballard, Morris, and Samartin, Sexton, and Thomason using hypergraph containers. Kind of in retrospect, like all these results here, this first 6 results, concluding with my unfortunate master thesis, they all kind of try to find this copy of H, kind of vertex by vertex, and because that's this uniform event, this event of uniform edge distribution kind of pushes you in that direction, but it turns out that's not the right way to go. And on the other hand, the proof by hypergraph containers is really neat, it's really short, but it relies on hypergraph containers, which are arguably not the first thing that you would come up with if you are trying to solve the KLR conjecture. So the goal of the new proof is to give a more accessible and sort of more direct proof, which one could have, which, for example, I should have come up in my master thesis instead of doing the K6 case on 80 pages. Okay, so let me move to the notepad. Okay, so here's what we have. So we have when H is bipartite, we have the probability of H not appearing in G and M, beta M for M large, and to get the same in the non-bipartite case, we need to condition on this event U epsilon. Now it turns out that if you prove this in a certain way, actually the same proof generalizes in this case. So this is what I want to discuss. So solving this contains, at least in this way, contains all the ideas to prove the K-log conjecture, but is marginally technically easier. So what I want to discuss is the proof of the following. So we want to count the number of subgraphs of Kn such that they are exactly of size M, and I will only do it for the special case of C4. So what we want to show is that this is at most beta to the M and square choose M, right? For M bigger than some C and to the 2 minus this 2 density, which is 2/3. Well, actually, so C is something that depends on beta. Now, instead of looking at this more general case, let me just look at the case where M is equal to this, and then let me also rewrite what this means. This is just 4/3. Okay, so this is the theorem that we want to show. Now, so what we want really to do is we want to count the number of C4 free graphs with exactly M edges. Here's the main idea. So instead of counting this, what we are going to count is this. Oops. Bigger line. What we want to count is this. And what I want to show is that if we can count this green, red C4s, we can count red C4s. I know what green and red means. Red means belongs to G, and green means belongs to D, where D is some dense graph. All right, so this is what we're going to do. And now the kind of the main lemma or the induction, if you like, goes as follows. So given some D set of edges of Kn such that the number of copies of C4 inside D is at least alpha n to the 4 for some alpha, then the following holds. Then we're going to look at a family of graphs, some G prime subset. Now, so the G prime does not lie in Kn, it lies in a subset of Kn, in particular in this D. Now G prime has M prime edges, and it has at most some, let's call it some lambda n to the 4 M prime or N2 to the 3 copies of this green red thing. So we want to show that the number of such graphs is at most beta to the M prime and square, which is M prime, some lambda. Now, what is this? This is the roughly the expected number of such copies. Okay, so if you compare, how do you zoom out? So if you compare what we want to show, what we do here is, so we strengthen this in two ways. So instead of just saying that our graph is C4 free, or in this case, where in this case C4 is this colorful thing, we want to count the number of such graphs G prime where the number of this copies is significantly less than expected number of copies. And the other strength is that we're not really looking at the whole Kn, we just look at this subset of K and D. But it comes with a big kind of relaxation is that we instead of looking at all edges being in G prime, 3 edges are in G prime and 1 is in D, and that will help a lot. So we replace one sparse edge with a dense one. Good. So let me continue. Now, what is this value here? If you do the calculation, this is just n square. Good. Now here's the main point. So let us denote with D of E the number of copies sitting on E, right? So the number of copies of this thing sitting on E, with E being this edge here. So what this tells us, if this graph, if we take a graph G prime which has at least this many copies, then we have that this is at least say alpha n squared with. Now, what we really like to say is that, well, actually most of these edges E in D, they belong to at least one such copy of this colorful C4. Now, this is not enough to say this. We could be very unlikely. It could be that there are very few edges which sit on a lot of these copies. But it turns out that to prove that many edges sit on at least one such copy, it's enough to bound, in a way, like the second moment of this. So we want to show that if this is also bounded by n squared, then these two imply that many edges in D sits on a copy of this. Okay. So in other words, if we have that this family of these graphs G prime which have few copies is very small, then also for all the graphs, or almost all the graphs which do not belong to this family, we will not only have that that they have at least some lambda n square copies of this, but with some extra effort, we will also have that many edges in D like linearly many edges in D, where linear means to the size of D. So order of n square edges of D, we'll see it on such a copy of C4. And the way you prove it is, and this is proven by a Roloruchinsky deletion method. Okay, now this is really everything we need to do the proof. All right, so how does the proof go? So instead of counting directly the number of C4 free graphs, we're going to count the number of sequences of graphs whose union is C4 free. So let B denote the number of sequences of graphs G1, GK, GK plus 1, such that two things hold. First thing is that C4 does not appear in G1 union GK plus 1. And the second is G1. So the first K graphs are reasonably small. So they are size M over 2 times K. And GK plus 1 the size M half. And now here's the main point. So what we aim to show is that B is smaller than beta to the M, and then just the total number of ways that we can choose such a sequence. So this first K graphs we can choose in this many ways, and then the last graph we can choose in this many ways. We don't care if these graphs are disjoint or not. We really just look at them as a sequence. This should really remind you of the multiple exposure and random graphs, where you sort of reveal the edges in rounds or in phases. And the reason why you benefit by looking at not at a single graph, but as a sequence, is that every time when you fix one such graph, you will know something about where the remaining graphs in the sequence have to live in order for the union to be C4 free. And this will give us this count. Now, if we have this, how do we show that the number of C4 free graphs is also small? The point is that that every C4 free graph with M edges, it gives many unique sequences, right? By many, that's some X, and therefore we know that the number of C4 free graphs is at most beta to the X, and if you play the numbers correctly, you get this is beta to the M and square choose M. Okay, so we get rid of like looking at single graph. Now we can look at the sequence, and let me show you how you benefit from looking at the sequence. So what we start with is, so we started with the set D naught being just the edge set of the complete graph. Now let's look at, zoom out a bit. Well, let's look at G1. So G1 lives somewhere here. This is G1. Now G1 has, so from now on, this whole set, this is a set of edges, not the set of vertices. So every time when I draw a blob, that blob is a set of edges and not set of vertices. So here we have edge 1, 2, 2, 3, say 3, 4. And then, for example, outside we can have an edge. We can have edge 1, 4. So fix some G1. Now let's look at all the edges which do not form C4 with some 3 edges from G1, and let us denote all such edges, the set of all such edges with D1. So everything outside of D1 will form a C4 with some 3 edges from G1, and everything inside D1 will not form C4 with any 3 edges from G1. And now repeat the same. Now here's the main point, that now let's look at G2. If G2 would look if this would be G2, then this edge would become red and we would have a C4, but that's not what but we are counting C4 free graphs. So for this sequence to be C4, we need that G2 is completely contained in D1. Right, now again, let's look at all the edges inside D1 which do not form C4 with some 3 edges from G2. Let's know this with D2. And again, G3 has to lie completely inside D2 and so on. Right, and we do this for K steps. And then finally, we know that this very large G2, GK plus 1 has to lie inside here. And this picture almost tells the whole proof. So 2 things can happen at the end. So either decay, so first thing is that decay has, say, n to the 4 many copies of C4. But what does this mean? That means that we have made a bad choice of GI being G prime way too often. So every time we pick a good G prime or good GI, we have that many edges in D sit on a copy of this thing. So whenever we chose a good GI, this set dropped, or this upper set shrinks significantly. And by significant, I mean like really something of order n square. And if you make this step, in case some constant, so if you make a successful step enough times, we will end up with actually set decay having potentially even just a few edges, but which means that this would not happen. So if this happens, that means that we made a bad choice or very atypical choice way too many times, which then accumulates to beta to the m in this part, and then it doesn't really matter how we choose GK plus 1. The second thing that can happen is that, well, DK has a little lower n to the 4 copies of C4. Right, but then what does it mean? Because C4 is a bipartite graph, and we know that the what do I want to say? So if we know this, then we know that decay has to be also very small. So if the set decay had order of n squared many edges, then we would have order of n to the 4th many copies of C4. But because we know that's not the case, that means that decay is really tiny. But now from this really tiny set, we need to choose a lot of edges. And right, and this is that shows that actually that this beta to the m comes together with this. And that's the kind of a very brief sketch of the proof. So this picture is the main thing to remember. That every time when we make a good choice for GI, this set shrinks a lot, every time when we don't make a good choice, potentially this doesn't move at all. And if in the end we still have a large set decay, or set with many copies of the graph we try to avoid, that means we made a bad choice too many times, which is unlikely. And if we made the good choices often enough, then we end up with a small set, but then that just leaves very few choices for this very last large set. And that is more or less how the proof goes. Now you might say, well, okay, that's assuming we have this lemma. Now, how do you prove this lemma? You prove it in exactly the same way, but now instead of counting the number of C4s where you have 3 red edges and 1 green edge, you count the number of C4s where you have 2 red edges and 2 green edges. How do you prove that? You prove that by looking at the case where you have 3 green edges and 1 red edge. And how do you prove that? By looking at the case where all 4 edges are green, but in that case there is nothing to show because of our assumption. Are there any quick questions about this? If not, I will go back to the slides. Okay, so that was quick, but the main point was this picture where the set D, where the rest of the graph has to live, where it shrinks. Okay, what falls apart when you try to apply the same thing on a non-bipartite H? So again, recall the very end of the proof. With the super exponentially, with probability super exponentially close to 1, this last set decay, or either this last set decay contains little o of n to the number of vertices of H copies of H, right? And this last set gk plus 1 has to lie inside. Now, if H was bipartite, this was enough to conclude that this decay is really small. And then by choosing gk plus 1, we get this beta to the m factor that we were looking for. If H is non-bipartite, then we cannot conclude this, and decay can actually be very large. So for what it's worth, I just noticed that this last set decay depends only on m half edges of G. And it gives us, and it has very few copies of H. Now, by choosing the constants differently, you can get that the set decay only depends on some epsilon m edges of G, right? And it has little of n to the v of H copies of H. Now, what does that remind you of? Rob, you're in the audience. Does that remind you of something?
So the removal lemma.
No.
Say it again.
So what we have is that if you choose the constants differently, we have that this last set decay depends. So it's a set which has very few copies of H, and it depends on only epsilon m edges of G. What does that remind you of? Can you unmute yourself?
Sorry, of a container or a fingerprint.
That's exactly that. Those are the containers.
Right.
Right, and this is exactly what you can use to give a alternative proof of the containers, or kind of following the reasoning along these lines. You can get a version of the containers, and for it's a one-page proof, and I can only invite you to look at the archive from last Friday. But anyway, this just shows that in the end, kind of containers and all these counting results are really tightly related. And even if you try to prove one without the other, they meet at some point. Okay, let me give some credits to the previous results. So this idea of narrowing down the choices of where the remaining your random graph has to live. So this goes back to the seminal paper by Rudolf-Ruchinsky on Ramsey properties of random graphs. Then it was taken further by Schacht and Samoti, and even a version of the Kähler conjecture, or the main implication of the Kähler conjecture in random graphs was proven in this way. Now, if you're familiar with these proofs, you will notice that what I taught is actually fairly similar to what all these results did. And in that case, you might be wondering what the main difference is. And the main difference really is that all these papers consider GMP, and here we kind of count what happens in G and M. There are many subtle differences, but this is really the sort of the main difference. So in a way, this first result by Rudolf-Ruchinsky already contains more or less all the ideas necessary to prove Kähler, if you look at it the right way. There is another result by Conlon, Fox, and Zhao where they very explicitly use this idea that you start with you want to count the number of copies of some within some reasonably sparse subgraph, and the way you do it is by kind of recursively replacing counting copies where all the edges lie in the sparse subgraph by counting copies where all but one edge lie in the sparse subgraph, and this one edge lies in the actual host, which is kind of more or less exactly what we did here. And the last few minutes, just some open questions. So there is a counting version of the Kähler conjecture by Gerke, Marcinich, and Steger, which says that not only that if you condition this uniform edge distribution, not only you will get one copy of H, but actually you'll get, at least, or you will get at least almost the expected number of copies of H. And this was proven in this paper for H being a complete graph, but M being significantly larger than what the conjecture states. And the version of a container by Sexton and Thomason and the proof that I just showed you, they give you sort of a weak version of this conjecture where you can't really show that you get 1 minus epsilon times the expected number of copies, but you can get at least sort of epsilon times the expected number of copies. And then there is another problem, which was actually the main motivation for kind of revisiting the proof of the Kähler conjecture, and that's what can we say about large graphs? So if you look at this conjecture, this C here depends on H. Now the question is, can we make this C not really depend on H, but on some parameter of H, like maximum degree? And then the question is, can we show that the probability of H not being G and M conditioning on a uniform edge distribution is at most beta to the M if H is not fixed, but has the number of vertices of the same order as the number of vertices of the random graph. The value of M here really comes from the Kähler conjecture for H being a complete graph on delta plus 1 vertices. Now, if sort of this is interesting because of applications, and in particular the size Ramsey numbers. So you don't really have to prove this sort of pure, clean Kähler type statement. You can add here any other conditioning which allows you to prove something of this form. So as long as it can be applied in this context or any other similar context, it's fine. And this was shown by Kocher, Kavarolu, Schacht, and Sem already for M being, again, significantly higher than what the conjecture states. So here, this term here is half of what it should be. And we recently verified this for delta equals 3. And that would be all. Thank you.
So thank you, Rajko, for this very enlightening talk. Could I ask everyone to join me now in thanking Rajko in this way, in this virtual way?
Thank you.
So in this, as Rajko suggested, are there any questions to the talk?
I guess I have a sort of question. So thanks, Rajko, for a really lovely talk. It's a really lovely proof. Just related to Julian's question earlier about the correct answer. So if I understand correctly, so it's sort of asking, so for C4, for example, like Faraday counted the C4 free graphs with M edges a long time ago. But I have to remember correctly whether that the construction for that is satisfying this property. So with David Sexton, we had this construction where you take a projective plane and then blow it up and then take a random subgraph, which sounds like it should still satisfy the property. Or am I being silly? Because the projective plane is, yeah, maybe I'm being silly.
No, so for bipartite graphs, you don't need this property. Like the whole,
Right.
For bipartite graphs, it just holds. So the point of conditioning on this uniform edge distribution is to recover this super exponentially small probability of failure, or another way to like identify what's the main cause of GNM not containing a non-bipartite H. Yeah,
so I'm just trying to guess what the answer would be. So I can't think of now what the correct example to think of would be. So would the idea to be to perhaps take something that's if you're a non-bipartite graph, take something that's extremal for a bipartite graph, blow it up, take a random subgraph, stick it into two parts of it. I'm a bit confused what I'm thinking of now. Is it reasonable to hope that there's some kind of conjecture like that, or is it totally hopeless? I haven't thought about it before, but
I haven't thought about it either. I got the question before, and I haven't thought about it actually since. It was, I think, the only result which replaces this beta with something explicit is this result by Yoji Balog and I think Mariam Sharifzadeh and Hong Liu, if I'm not mistaken, where they look at the probability that an M element subset of integers 1 to n is K arithmetic progression free. And there they do replace this beta to the m with something that's I'm not sure if it's correct, but at least it's a kind of explicit function. But yeah, I don't actually know what the right answer should be. I think it's interesting, but I no idea.
I guess I can ask another question if no one else wants to. So for this delta equals 3 result at the end.
Yeah.
So is the proof of that? Is it related? Is it somewhat similar? Can you say something about that?
To the proof of the Kähler conjecture.
Yeah. So to the ideas you were mentioning today.
Yeah. No, not at all. So that goes back to this kind of vertex by vertex embedding. And then if you do it vertex by vertex, at some point the kind of the candidate sets will become too small. So then the idea is that instead of blindly doing it really vertex by vertex, you kind of split it into blocks, where each block is something simple like a cycle or a induced cycle or a path. And then you argue that you can embed it block by block. And you can do it and doing it for delta equals 3 is actually then it has some resemblance with this initial effort to prove the Kähler, where to prove the Kähler for K4 in this vertex by vertex manner, you can do it, but you have to do some gymnastics. And this kind of has a similar flavor. Like you can do it, it's not terribly technical. It's not too difficult once you have all the kind of details figured out. But I think delta equals 3 is kind of as far as it goes. Maybe you can do it for delta equals 4, but it's it just feels a bit pointless. Right, and then that kind of the idea is, well, to even have some hope to do it for a general H or bounded degree H, at least one needs sort of a reasonably straightforward proof of the simple case where H is a fixed graph, and then that's how this proof happened. But no, it has nothing to do with how we did delta equals 3.
And is there any hope of using this new magic sunflowers stuff to, because you know your H is huge, right? So
that's my hope, that this new ideas would inspire people, but then that goes kind of in direction of maybe instead of trying to prove directly some kind of a Kähler type statement, maybe universality is the next natural thing to do. And the sunflower proofs, they I mean, for a good reason, they will not give you the correct failure probability to do a union bound or something like that. So I think that doing universality instead of type problem instead of the scalar type problem is probably more natural, and should be significantly easier or somewhat easier. Maybe. But yeah. So the hope is that one should not use the momentum of having these new breakthroughs and kind of revisit these problems.
Thanks very much. Thanks again for a lovely talk.
Thanks for the questions.